So, what I neglected to talk about in the previous lectures is exactly how we construct manifolds. Because all I've only done, let's say I have a circle, S1, all I've done is specify the set that identifies it, but I never really gave you guys the concrete way of actually constructing it. Namely, what exactly is an atlas? So this is what we're going to answer in today's lecture. What is an atlas? Now, an atlas, formally speaking, is a collection of charts. So, definition. An atlas is a set of charts that cover a manifold. Of course, recall again that a manifold is a space that locally resembles Rn or C. So, if you guys recall the notion of a cover in topology, an atlas is basically a set of those. So if I have a bunch of subsets, so if I have a space X, and then I have a bunch of subsets mu alpha, where alpha indexes the sets, alpha is part of an index set J. And then J could be a set like 1, 2, 3, 4 to signify what exactly are the subsets. If the union over all alpha of these subsets is precisely X, then mu alpha, the set mu alpha, is a cover of X. Now, the notion of a cover is similar, or at least atlas is similar to the notion of a cover, in such a way wherein really it's a collection of charts. But the thing is, charts are not precisely subsets, but these are maps between portions of our manifold and two-dimensional or three-dimensional Euclidean space. So if I have an F space, so this time we're applying this notion. So if I have a manifold, an F manifold, say maybe a Femboy donut, right? I have a Femboy donut. What is its atlas? Well, of course, it's precisely a Cartesian product. This is T2, so it's precisely x squared, y squared, minus r squared, or 1, times x squared plus y squared minus r2 squared equals 0, such that, well, these things, x, y, r1, r2, are inside the four-dimensional F space. So it's just we're just taking four distinct outputs or four distinct inputs. Now the specified maps that we have here is precisely this function over here. We could think of it as, I suppose, taking some portion of this, a point here, and then mapping it onto three-dimensional Euclidean space. So the first map is this one, and another map is this one, which sort of take their products together in order to get this, right? So I know this sort of gives an annulus, but it's really this over here, because what we're saying is that we're taking the sort of product between two circles. So you recall that a manifold Ft2 is equal to, by definition, a Cartesian product between two Femboy circles, Fs1s. And these are two, basically, yeah. So I mentioned in another video that we can think of the set, or at least this generating relation, to be the maps. So yeah, that's one example. And a while ago, yeah, I'll give you guys the example, x squared plus y squared equals r squared. This over here is a chart of a circle. It's part of it. Well, actually, it maps the whole thing onto R2 by precisely giving us, like, if I have an interval 0, 1, open, I identify the points, I take these two and then I connect them together to form a circle. But what we really do with this relation, if I call this, like, if I have a relation mu that implies this relation, mu sends this interval to R2. And this interval here is precisely a subset of a circle. A full circle would be a closed version of it, such that, of course, 0 equals 1, which is identify the points. Now this time here, we have a subset of it, and then we map it onto R2. And then, I suppose we just take a mod of R and Z, entirety of R, in order to actually construct the thing. Okay, so charts. So what other examples? So there's this analogy, or a great visualization of the entire thing, and is that if I have, or this map here, let's make a picture of it. So I have a circle. And so, alright, I have 4 versions of the real plane. 1, 2, 3, and 4. And then what charts do is basically take portions of these and then map it. So mu is a map this time. It's not precisely a subset. It takes it to a portion of the sphere, or at least these subsets of R, and then they cover it. So a small portion here. So this interval is taken, and then it covers a subset of the circle. So we grab these subsets too, and then they also cover this part. So there might be some overlap though. This, and then this covers that. There. So let's go here. Please sit down, Jeff. Covering the board. So this is a good visualization of a chart, or at least, yeah. So it is mu1, mu2, mu3, mu4. The collection mu1, mu2, mu3, mu4 is an atlas. Okay. So another analog of this would be, I guess, if we're going to construct a sphere. You would take 4 a cube, or rather faces of a cube. So you have different versions of R2. So 1, 2, 3, 4, 5, 6. 6 squares, or 6 R2s, or R2 planes. And just so you know, these aren't the actual R2 planes. These would extend infinitely outwards, but for the sake of visualization, we're just going to keep it like that. And I won't show the front and back, but it's implied that those exist also. So R2, and then mu, I guess, covers it, or like molds it, or takes a subset of it, a small square, and then pushes it onto the sphere to cover it, and that gives us the atlas as well. Okay, so now to femboyize it, what we just need to do is, morning Kyle.
Yeah. Morning.
Just need to FR, I suppose. So if you recall from algebraic femboy theory, I know this is a bit circular. You're supposed to learn this before femboy theory, but you guys will learn this. Yeah. So we just make a bijection between the fundamental set of all femboys and then the real. And then the real set, it's possible to make this construction. Of course, and this is FS2. And this would be FS1. Now, what about, like, I know that this is only a surface, but what about a volume? How do we generate a volume? Well, the thing is, volumes are, they may be considered manifolds, but that's not really the focus of this course or topology in general. What we're concerned with is surfaces. So, mostly focus on hollow shapes and how to construct them out of these. So, that's a visualization of an atlas. So, the combination of the maps that take subsets of these planes onto and then wrap the sphere with those subsets. The collection of those maps is an atlas. And yeah, I know you can make a manifold without specifying its atlas, but if you have a very complex manifold, let's say a Calabi-Yau manifold, it's going to require some charts to allow us to understand or study it mathematically, because it has an intrinsically 7-dimensional structure or 6-dimensional structure. So for surfaces or curves that we can visualize in R2 and the R3 space, I suppose you kind of don't need an atlas. You just need a nice relation that contains x, y, and z variables, or an r variable, or maybe you can use the exponential function. You can extend it into the complex plane in order to do or construct the manifold, or you can have the entire space be the manifold. Of course, you could just be a tuplet, but of course the entire space of R is not a manifold itself. It's just that it is that. So yes, very short lecture. Just needed to specify what exactly an atlas is, and yeah. So it's a collection or set of charts, and charts are a bunch of maps that take a subset of F space or R space, and then map it onto a cover, either open or closed, of a manifold. So yeah. So another example. Let's make another example. Let's make the definition more precise by specifying what exactly a chart is. So I know I already mentioned this. Chart is this mu1, mu2, mu3, mu4. But let's make it more specific. Okay. A chart is a set, is a map, or a set of maps, which I will call mu alpha. So it's not subset now. It's now maps that take a subset of Rn and map it onto an open cover of X. So A is a subset, and then we have, this time I will call it, let's call it omega. So omega, where omega is an open cover of X. Or if we want to state it in terms of our theory, so, or a mu alpha and family of maps, or just one map, it could just be one map, that maps a subset A of F space, and then takes it onto our F manifold, or an open cover of our F manifold. Where of course, if F is our F manifold, the union over all values of this open cover is precisely F. So the open cover. So there, this is our precise definition of what exactly a chart is and what exactly an atlas is. So, questions? Any questions?
It's a chart, right? And the last one you discussed, what's the cover like the atlas?
Yeah, no, atlas is a collection of the things that take Rn or like say flat space, and then it maps it or takes it or like wraps it around the shape or the manifold.
Yeah.
Yeah.
Got it.
So yeah. To make it more precise, I suppose I have a bunch of a collection of points in F space. So it's gonna be Fn. Sorry. Fn space. So it could be a quintuplet of points that abstract femboys, and then we map them onto this F space. Yeah. So that's one way to specify what exactly a manifold is. Because if you just say, a space X with its topology or a topological space is a manifold, that's not enough. Sometimes it's not enough. I mean, I suppose it's enough. You have, of course, R with the discrete topology. That's already a topological space, but not really a manifold. Well, on the other hand, S1 is a topological space. Well, under the subspace topology, and it's radius over R. This over here gets a topological space and it's a manifold. But at the same time, we do have a generating atlas of this, but we don't have a generating atlas for R. All we have is just a set, well, x, x1, xn, such that, well, these things, x, x1, xn is in Rn. That's all we have. So it's not really, it doesn't really have a generating relation, so it's not a manifold. So, that's a good place to stop.